All right, everybody, you waited a long time for this. Finally, the weight versus mass. What in the world is the difference? They seem like the same thing, and we use them interchangeably, even though they are quite different from one another. Well, here we go. So weight is the force due to gravity. It's actually a force. It's a field force. What means that by the field is it's nothing really pushing on top of you. It's not like an elephant sitting on your head or anything. It's actually a field, like a force field, yanking you towards the center of the earth. We'll learn later on that we're also pulling on the earth just as hard, and that's a third law interaction. That's coming up at a later time. All righty. So it is directed downward, varies from location to location. So it's a force. Weight is a force. Mass is the amount of stuff, which even if you ask a physicist, hey, what's mass? That's kind of a complicated thing. So it's really an inertia is what it is. Okay? Something that's twice the mass is twice as hard to accelerate or twice as hard to slow down, is twice as hard to shake. It's got twice the amount of inertia. But what's going on? Why is it twice as hard to shake? Well, we know it is anyway. So it's a measure of the inertia. This is a pull of gravity, the weight. The mass is the measurement of, for better term, stuff. Okay? So FMUS, what we use Newton's second law. We're going to use something very similar because weight is a force, mass is the amount of stuff, and g is the acceleration due to gravity on whatever surface you may be on, some other planet or moon or asteroid or whatever. So it's very closely related. Now we're not going to use a W, we're going to use an F sub g, meaning gravitational force. This is how you find the weight of something. So mass and weight are similar, but to make it a weight, you got to have a little g thing, at least mathematically. So your mass is your weight per the g thing, the force of gravity per the g thing, a measurement of this inertia. Okay? Some people separate this mass, be inertial mass, and that's gravitational mass. It's all mass, the amount of stuff. Okay? All right, what's the weight of a 10-kilogram block? Well, see, this is what gets confusing. You ask somebody not from this country what the weight is of a block, they're going to answer kilograms. Oh, hey, what's your weight, dude? My weight is 70 kilograms. That's actually not a weight. It's actually a mass. Okay? So what's the weight of a 10-kilogram block? Well, on Earth would accelerate this at 9.8 meters per second squared. And the reason is because the Earth pulls on everything at the surface of the Earth with 9.8 newtons per kilogram. Okay? So if I back that up over here, so Earth pulls on everything with 9.8, this G thing, newtons per kilogram. Kilograms you cancel out and you're up in the newtons. Or meters per second squared. It turns out it's the same unit. Okay? So a newton per kilogram is the same thing as a meter per second squared. There's no difference between a newton per kilogram and a meter per second squared. It's the same unit. So there you are, guys. 98 newtons. Isn't that thrilling? What's the mass of a 64-pound block? Well, now we're solving for the M. So if we're solving for the M, that's the W over the G. The weight is 64 pounds. Divided by the G thing, well, 9.8 meters per second squared is 32 feet per second squared on planet Earth. It's one and the same measurement, just a different unit. There it is, guys. 2 slugs. So here's the story. Mass is the same wherever you are. You can take a mass from this planet to the moon, and it's the same mass. But your object weighs different here on the Earth than it does the moon because there's a different gravitational field. So weight can actually vary. So on Earth, something that's being pulled on with 98 newtons will accelerate at 9.8 meters per second squared. You go further away from the Earth, and it might only be 49 newtons because the pull of gravity would be less going up, and therefore a lesser acceleration. But the mass is the ratio of the two. 98 per 9.8 is the same ratio as 49 per 4.9. It's the same ratio, the same mass. So the mass doesn't change. It's just 10 kilograms. Whether you do 98 newtons per 9.8 or 49 divided by 4.9, it's all the same mass, same amount of stuff, but the pull of gravity is different. So weight can change, mass does not. Unless you cut something apart, then it's going to have less mass. So on Earth, 64 pounds, it's going to accelerate 32 feet per second squared. Go further away, it's half the weight, half the acceleration. It's still 2 slugs. 64 divided by 32, still 2 slugs wherever you go. All right, so you can describe things by weight or mass. So here's the story, guys. If we go back a slide here, we don't live way up here or there. This is where we live. So it turns out anywhere on the surface of the Earth, this thing is going to weigh 98 newtons. It's going to be pulled on 98 newtons anywhere on the surface of the Earth. And it's also going to have 10 kilograms because that doesn't change anywhere. So because we live at the surface of the Earth, anywhere on the surface of the Earth, this mass is still going to be 98 newtons. This 2 slugs is going to be 64 pounds anywhere on the surface of the Earth. So because of that, yes, we can get away with talking about things. Something that's twice the mass is 20 kilograms. Something that has twice the mass is going to be 196 newtons in terms of weight. It'll be twice the weight. Twice the mass is twice the weight. That's why you can get away with talking about things relative to the Earth. Because if you double the mass, you will double the weight. Alrighty. So weight is a force. Mass is the amount of stuff. Alrighty. So conversion is made with the second law. We can also use this thing. Remember I use an F sub G because most people do. It's a derivation of Newton's second law. Alright, inconsistent usages. Alright, we got to keep rolling here. In America, objects are often referred to by their weight at a point where gravity is equal to 32 feet per second squared. So an 800-pound force pulls a 3,200-pound car. We know how heavy this view of the mass is relative to other things just by the weight. But in reality, we don't care about the weight being pulled downward if we're accelerating forward. We really care about the mass of that thing. But I mean, it works fine. We understand what's going on. But technically, it'd be better to talk about the car being a 100-slug car, which is not how non-physicists talk. Thus, when an object is described as a object, remember to divide by g to get the mass. Okay, so if it's in terms of force, you can take 32 divided by the 32 feet per second squared. 3,200 divided by 32. That's how you get your 100 kilograms or 100 slug car. So in metric units, here's the nice thing, guys. We're not going to use the American system anymore. We're pretty much done with the American system after that because it's just a lot easier to stick with one type of unit. So we're going to stick with the kilogram for the mass and weight for the newtons. So if a chemist wants to weigh out a 200-gram certain element, also you want to hear about a 10-kilogram load as if it were a weight. We use them interchangeably because we know what they mean, so we don't always use them correctly. Like the chemistry is going to weigh out this. Well, the weight's not 200, the mass is 200. And this is 10-kilogram mass sometimes is talked about a weight, even though it's a mass. That's what we're talking about being inconsistent. Okay? But that's how we talk. Not just Americans, people around the world do that. Okay? So kilograms is a mass, not a force. There's no direction. It's a scalar amount. This thing is the same mass, 10 kilograms. Anywhere you put the thing, on the moon or anywhere in this universe, it's got the same mass in no particular direction. The weight varies depending on where it's located in the universe, though. So in physics, second law, many applications, absolutely necessary to distinguish between weight and mass, because it's going to screw you up. That's why we're spending so much time talking about this. Is a lot of times you're going to mess up where you put the mass. You put it in for the force, or you put a force in for the mass. They are two different things. One's the amount of stuff, the other one's a pull of gravity. And you don't want to screw it up. Mass is in kilograms, weight is in newtons. In the American, United States customary unit, mass is slugs, weight is pounds. Okay? We give a preference to the metric system here. All right. So what is mass? Oh, it's been a while since I clicked onto this thing. This may not be the thing to go to. It'll be up in 17 minutes, don't worry. Buffering. We're buffering here. We're buffering. We're buffering.
Welcome to the Universe Effect. I'm JP, and today we will tackle the age-old question, what is mass?
Need a subwoofer for that.
Let's figure out how to calculate mass. So the weight or force of gravity is approximately rest mass times acceleration due to gravity, which is about 9.8 meters per second per second. Use the scale in your bathroom to measure the weight, and bada bing, you have the rest mass. So this is how we measure mass, but we still don't know what it is. I remember another equation that Einstein helped us with. Energy equals mass times the speed of light squared. This equation is a bit misleading because it only applies to objects that aren't moving at all. The energy mass equivalence equation for a moving object is this. Look familiar? Yes, Pythagoras is back to help us again, so let's make a right triangle. Okay, so if you don't know what momentum is, it's approximately mass times velocity. By adding velocity to our equation, we can find the energy of a moving object. This is further reinforced by the fact that if we make velocity go to 0 in our triangle, one of the sides disappears and you end up with two equal sides, E equals mc squared. The important thing here to remember is that mass is not converted to energy. It literally is energy. Okay, now let's look at an example. Say there's an object moving through space. If it's moving, it has some kinetic energy, and since energy and mass are directly proportional, when energy increases, so does mass. Yes, when something is moving, it has a bigger mass. Actually, most of the mass of an atom comes from the kinetic energy of the quarks making up its protons and neutrons. Let's talk about atom bombs. There's this interesting element called uranium-235. When a neutron is shot into its nucleus, it creates a reaction where the atom splits into two different atoms. Then 3 extra neutrons and a lot of energy is released. Why so much energy? It's because E equals mc squared. The speed of light squared is a huge number. It's about 8.99 times 10 to the 16th. So when the chain reaction starts, it causes a huge explosion. Nuclear reactors don't explode like an atom bomb because the reaction is controlled with the water inside the reactor. The heat of the reaction turns the water into steam, which pushes a turbine. We could go on all day about mass and energy, but the simple fact is we don't fundamentally understand what they are. Maybe someday one of you will figure out the biggest mystery of the universe. Share your thoughts and ideas in the comments below and we'll be happy to discuss them with you. If you like this video about mass and energy, don't forget to check out our other videos and the Universe Effect podcast. If you're the smartest person in the room, then you're in the wrong room.
Oh, man. I'm in a room by myself. So I'm not only the smartest person here, I'm also the dumbest. Hey, what you never learned about mass. Alrighty, this thing is so slow to get rid of. See if I can pop that out of there. And see if I can get back to... There we go. Alrighty. Oh, we're going to go ahead and pause here for example 5 and do this another time. Alright.